Okay, YouTube, in this video what we're going to do is we're going to further explore plotting points in polar coordinates. And that is to say, when we are given a point, say in the polar coordinate plane, recall that instead of giving you an xy pair, instead of what we're providing there, we're providing this r theta pair, which is telling us two things. First of all, it's telling us from the pole that we have located at the origin that our point is r units away from the origin. And also from the polar axis, which is located on the positive x-axis here, we're rotating in a theta direction here, whatever theta is. And so what I want to confront in this video is this the only way that we could represent a specific point? That is to say, what if I had a point here, and this point was in a pi-4th direction and 2 units away? That is to say that I know that r is 2, and I know that this angle here is pi-4ths. We would have some representation of this point like this. 2 comma pi-4ths. My question to you is this the only way we could describe this point? Now thinking about this, in terms of an angle here, is pi-4ths the only angle that could be heading specifically in this direction here? And so I guess kind of to explore this a little bit here, what if we switch our color here? Recall that just because pi-4ths does go in that direction doesn't mean we can't have another angle that would be pi-4ths plus 2 pi, and it would be going in the same direction. And so if we were to have some new point here, say 2 comma pi-4ths plus 2 pi, I don't mean to write a comma there, plus 2 pi, you would see that really this right here is coterminal to the original pi-4ths. And so what this means is by leaving r alone and by taking our angle and adding on 2 pi, we can always obtain a point that's in the same spot. And so over here on this diagram that we have right here, we could also illustrate it this way, and I need to write that right there. But we could say that another way of representing this very same point would be the same r value, the same distance, but our original angle plus 2 pi, because what that would be is just a coterminal angle. Now, would that be the only way of representing this? And this, unfortunately, is not. We would say, actually, fortunately, is not. I would say that what if we were to have an angle here, pi-4ths, is what we started with here, and we're saying we're going 2 units outward in that direction. Remember that our r value can be negative. And so what this means is if we were to maybe imagine that we had some other angle here down in this quadrant here, and if we were facing in that direction, how could we walk to get to this point back here? We could see that we could walk backwards 2 units from facing in this direction. And so another way to really represent this point would be this way. We could say walk backwards 2 units, but what I want you to do is be facing the exact opposite direction from pi-4ths. And so the question really here is, well, how do you get to the exact opposite direction of pi-4ths? What we can do is we can add on 180 degrees, or we could just add on pi. And so the note I want to make here is this. This is the opposite direction of pi-4ths. Because we added on or subtracted off a pi to that angle measurement, we would have to be facing the exact other way. And so the other way of representing this very same point here is with a negative r value, but what we could do is we could say add on 180 degrees to our original theta value, or pi radians here. And so with this representation right here, these two representations, what I want you to see is basically that with rectangular coordinate system, there's only one x and one y that gets you to a point. But with polar coordinates, there are several different r theta pairs that we can give. And so what we see here is kind of a generalization of what we just described on the right, but basically that if you wanted to get another point representing the same original point but using different r theta values, then what we could do is we could add 1 revolution or 2 pi radians to the angle, and that would not change the point's location because we're going the same direction and the same distance r. Now the other possibility we said was we could walk backwards r units in the opposite direction but be facing the opposite direction, okay? So basically, we would have to take our original angle and face the opposite direction, but then walk backwards r units. So we can see that adding a half a revolution, or pi, or 180 degrees, to the original angle, and then replacing our original r with a negative r, doesn't change this point's location. And so, more generally speaking, you can see in this yellow diagram here, it says that our multiple representations of points are given thusly. And so that if n is any integer that we want, that is some whole number that's positive or negative or 0, we say then the point r theta could be represented as r comma theta plus any multiple of 2 pi, or r negative r comma, theta plus pi plus 2 pi n. Now what I want you to see is this. We would say that this makes it coterminal, oh my goodness, that doesn't even look like coterminal, to the angle, and I'm going to say theta plus pi. Because what we're doing is we're saying take the original angle, face the other direction, make a half rotation, but then add on multiples of 2 pi n. And so basically what this means is we could add on 2 pi or subtract off 2 pi as much as we want, and we're going to get a coterminal angle. And if we want the opposite here, the opposite of r, we would just add on pi first and then just say anything coterminal with that. So what I want to practice in this video is essentially this. I want to give us a point, say this point 2 comma pi thirds, and what I want to do is find another representation of this point in which these things are true about it. And so the first thing I'm going to encourage us to do is draw a picture. Whenever we're given a point, either in rectangular or polar form, we should always draw a picture of this. And so what we know is that this angle here, if we're going to do this, say in radians or degrees, we'd say 2 comma 60 degrees. We know that it's going off in a 60-degree direction. And what I'm going to do is I'm just going to pick a point along this line right here, and I'm going to say, hey, look, you know, r from 0, 0 to the origin, from the origin to this point is a distance of 2, and we know that this is 60 degrees right here. Or we should rightfully say that this is a pi thirds because that's what we started with. So here's our point right here. We're going to say that this is 2 comma pi thirds. Now, that being graphed, we want to say, could we find another point where r is positive, but we want our angle to be between 2 pi and 4 pi? And so right now, basically, we could say that 0 to 2 pi would lie between here and here, but 2 pi to 4 pi, that would be another full rotation. So what could we do at this point to keep r the same, but then get an angle that's bigger than 2 pi? Well, what we could do is we could just add on 2 pi to this right here and keep our r value positive. So for letter A, essentially what we're going to do is we're going to say that we would have the same r value, which is 2, but we're going to take our original angle here, and because we want it to be bigger than 2 pi but less than 4 pi, we'll just add on a 2 pi rotation, which does mean we need to find a common denominator here. We have pi thirds plus 6 pi thirds. That would give us a total of 2 comma 7 pi thirds. Now, had we done this in degrees, I just want to show you this here. We had started with 2 comma 60 degrees, and really all we did was we said let's add on 360 degrees to this. Well, we would end up with this 2 comma 420 degrees, and you can clearly see that 420 degrees would still terminate along this terminal side, but also be between 360 and 720 degrees, or 2 pi and 4 pi like we wanted here. So we'd say here's our alternate point, or rightfully we should have done this in radians. So let's take a look at letter B here. Letter B, we have this point 2 comma pi thirds, but what we want to do is now get another point where r is negative. So we would say that, okay, well, we're walking backwards now, but our angle is between 0 and 2 pi. So the question is, well, what could I add or subtract to pi thirds that would make it so that when I walk in the backwards direction, I still land on the same point? We would say that we would have to add on pi to this original angle, or subtract off pi to turn a half rotation. So what we're going to do is we're going to take our pi thirds, and because we want it to be bigger than 0 but less than 2 pi, we'll just add on a pi here. And likewise, we're going to need a common denominator again. So we get negative 2 comma pi thirds plus 3 pi thirds, but we would get instead negative 2 comma 4 pi thirds. And so you could see that if we were to graph 4 pi thirds, by the way, that would be, let's see, 1 pi third, 2 pi thirds, 3 pi thirds, 4 pi thirds. Here would be this direction, but you could see that walking backwards 2 units would still put us at that original point right there. So that's good. We would say that here's our alternate point right here. And then for our last one here, we want one where r is positive, but our angle is between 0 and negative 2 pi. So what we could do is the same thing we had done initially, but instead of adding on 2 pi, we'll subtract off 2 pi. So for C here, we'd say starting with the point 2 comma pi thirds, if we want our angle to be negative, we'll say the same r value, but we'll take our pi thirds here and we'll subtract off 2 pi, or 2 pi wholes. And so to keep writing this here, we'd say 2 comma pi thirds minus 6 pi thirds. Okay, so this would give us here 2 comma 5 pi thirds negative. And we could see that if we were to graph that, negative 5 pi thirds would have wrapped around this way, and we would have been walking still 2 units outward from there in a positive 2 direction. So we'd say here is our third and final point that could represent the same thing as right here. So what I want you to do is I want you to pause this video and take this point that I've given you here, 5 comma pi fourths, and I want you to, first of all, graph it. but then go and find 3 other points that satisfy these conditions here. So go and pause the video and give this a shot. Now after you've given this a shot, we could take a look at your solutions here, and we would see that in a pi force direction, we would just say, just picking a point here, it doesn't have to be anything special because we can always say what distance it is away. But we'd say this is our 5 here, and this is our pi force that we see here. So this is the point 5 comma pi force. So this time, let's try to work a little bit more quickly. We say if r is positive and our angle is between 2 pi and 4 pi, then maybe if our r is positive here, what we're doing is we're taking our original r value, keeping it the same, of course, but we're taking our original theta value, and we could just add on 2 pi to this. So now 2 pi, I happen to know that 2 pi is the same thing as 8 pi fourths, and so what we really get here is 5 comma 9 pi fourths would be the same point as what we started with here. Looking at letter B, if we want r to be negative and we want our angle to be between 0 and 2 pi, well, negative r value, first of all, would mean we have to switch our 5 to being negative. And because it's negative, it would mean that we would have to move away from our original angle by a half rotation or by pi units. So because I want my angle to be between 0 and 2 pi and not negative, I'm not going to subtract pi off of this. I'm going to add pi onto this. And while we're at it, why don't we go ahead and call this 4 pi fourths. That way we can say that this is negative 5 comma, and our 4 pi force plus pi force would give us a 5 pi force radian measurement there. And then so for letter C, we want r positive, but we want our angle to be between 0 and negative 2 pi here. And so if r is positive, certainly we'll go with our positive 5 here, but instead of adding on 2 pi to our original angle, let's do our original angle minus 2 pi, which is minus this 8 pi force that we kind of dealt with up here. And we could see that really we would go 5 units in a negative 7 pi force direction and still wind up at the same location as what we started with. So points in the polar coordinate system are not unique. There are infinitely many points that can describe the location of one individual dot. Cheers.